This is part 2 of 3.1. Now we're going to look at what we call classical probability. This is probability that you're used to, like tossing a coin, rolling die, picking cards out of a deck. What's going to happen is we are going to, depending on the event, so let's say the event is getting a heads, that's the number of outcomes where you get heads is going to go in the numerator in the top of the fraction, and then the total number of outcomes is going to go in the bottom, in the denominator. And so we call this the probability of event E, and we're going to do some problems and that'll make more sense. Okay, so we have a six-sided die. We know with a six-sided die that each side has a different number on it, right? And so our outcomes are 1, 2, 3, 4, 5, or 6. So we have 6 total outcomes. That's going to be our denominator. And then we have different events here. So for event A, they want to know the probability of rolling a 3. Well, there's only one 3. Right? So there's only one chance. If we roll a die just the one time, there's only one chance that we would get a 3. So the 1 is going to go in the numerator. Our total number of outcomes, which is 6, is in the denominator. And so the probability would be 1 over 6. Okay, for event B, this is the probability of rolling a 7. Well, there's no way to roll a 7. It's not a 7-sided die, it's a 6-sided die. And we're only rolling once. So there are 0 chances of rolling a 7. So 0 is going to go in the numerator. The 6 is going to go in the denominator. But of course, dividing 0 by any other number except 0, we get 0. And so the probability of rolling a 7 is 0. All right, finally, event C is rolling a number less than 5. Okay, well, we have 4 choices. If it's less than 5, it's not including 5, we could have 1, 2, 3, or 4. So we have 4 possibilities of rolling a number less than 5 out of 6. We do have to simplify that. Remember, you can put it in your calculator, especially if the numbers get big, to simplify. But you can also see that they're both divisible by 2, and that gives us a probability of rolling a number less than 5 would be 2/3. This page is just showing you the work again from the book. So if you guys want a little more explanation. All right, let's play some cards. So I have all of the playing cards here. We have hearts, diamonds, spades, and clubs. And within each of those, you have an ace, king, queen, jack, and then 2 through 10. Okay, so these are all of our cards. A standard deck has 52 cards. That's what we're going to be using, a standard deck. So 52 is going to be our denominator because that's our total number of cards. So the first one is the event D is selecting the 9 of clubs. Well, the 9 of clubs, there's only one card that is the 9 of clubs. And so our probability would be 1 over 52, right? Because there's only one card that's the 9 of clubs, but that's out of all 52 cards. Okay, event E is selecting a heart. Well, we have 13 hearts, right? Lucky 13. We have 13 hearts out of 52 cards. And if you reduce that or pop it in your Casio and let the Casio reduce it, you get 1/4. So the probability of selecting a heart would be 1/4. All right, event F is kind of crazy. It says selecting a diamond, a heart, a club, or a spade. Well, that's all of the cards, right? If you take, if it's going to be a diamond, a heart, a spade, or a club, you have 52 cards that meet that criteria out of 52 cards, and so you get 1. That's okay. We can have a probability of 0. We can have a probability of 1. We can have a probability anywhere in between, but we can't be less than 0 or greater than 1. All right, a little more vocabulary. Empirical probability or statistical probability is when we look at observations. So maybe we surveyed people or we watched people coming through the door to see what color their hair was. And so what we're going to do is whatever we're looking for, the event E, however many observations of event E, that's going to go in the numerator on top. And then our total number that we observed or that we surveyed is going to go into the denominator. So a lot like what we were doing with the classical, but this time we're doing observations. All right, so a company did an online survey and they asked adults to determine how they read books during the past year, if at all. They surveyed 1,490 adults. So that 1,490 that they surveyed is going to be my total. That's going to be the denominator. The pie chart shows the results. Note that digital books include ebooks as well as audiobooks. Okay. What is the probability that the next adult surveyed read only print books during the last year? Okay, so only print books would be right here, 578. So that is going to be my numerator. That's going to go in the top of the fraction. I did over here add them all up. That's because sometimes the problem doesn't give you the total. If they did not give me the total, I would have to add all the pieces of the pie together to get the total, but they actually gave me the total. So I'm going to take 578 divided by 1,490, and that gives me 0.38. That's the probability of the next adult surveyed is going to read only print books. Now you have to be really careful with MyMathLab because sometimes they want a fraction, sometimes they want a decimal, sometimes they want 2 decimal places, sometimes they want 4. So you really have to read the fine print. This is just the problem worked out again. This is from the book. All right, so now we have a frequency distribution. We're used to this. We have ages in the first column, so their age ranges from 18 to 22, 23 to 35, and so on. And then the frequency. They were doing a phone survey, so they asked them how old they are, and then if they used social networking. So this survey is showing the ages of people who use social networking sites. They surveyed 975 people, so that would be in the denominator. The frequency distribution is shown in the table. What is the probability that the next user surveyed is 23 to 35 years old? So we're just going to go to that line. That would be the second line, 23 to 35. It says that 312 adults that were surveyed are ages 23 to 35. Sorry. So the 325 is going to be in the numerator, 975 is in the denominator. Pop that in your calculator and you see that the probability that the next user surveyed is 23 to 35 years would be 0.32. All right, so this is again just the problem worked out. So you don't need to know this for any quiz or test, but I just want to show you the law of large numbers, it's called. So what happens is if you, like we know, if we toss a coin, we know if it's a fair coin that we have a 50-50 chance of getting a head, right? So that means half the times I throw it that I should get a head and half I should get a tail. The problem is if you only throw it 10 times, it might not happen that way. You might get 6 heads and 4 tails, or you might even get 7 heads and 3 tails. I mean, it happens. But if you toss it 150 times, you have a pretty good chance of half the times that you see a head and half the times you see a tail. If you go up to 15,000, then you're definitely going to. So that's the law of large numbers. If you have a very small experiment, you might not see exactly what you think you should see. That's why this graph is kind of looking all over the place. That's because when it's small, it might be off a little bit, but once you have tossed that coin many times, you're going to be close to that theoretical probability of 0.5 or 50%. All right, now we get down to subjective probability. So this one is a little tougher. It's based on intuition or an educated guess or an estimate. So, like if you go in to see your doctor might say you have a 90% chance of full recovery. He doesn't know for sure, he or she, but they're basing their information on patients that they've seen over their career and studies that they've read. So, that is an educated guess. If a business analyst predicts that the chance of the employees of a certain company going on strike is 0.25, again, that's subjective. He thinks that's what's going to happen based on what he's hearing or based on the economy, but it's not based on actual data. Okay, so we have three different kinds of probability. We have classical probability, that's like tossing a coin, rolling a die, picking a card. We have empirical probability, that's if we're doing a survey or if we're observing. And then subjective is based on intuition, educated guesses, or estimates. So a few of your homework problems are going to ask you which kind of probability you have. So the first one is the probability that you will get an A on your next test is 0.9. Okay, well, that's subjective. It is based on how hard you're working, right? If you're doing your homework, you're doing your quizzes, you're doing your practice quizzes and homework before you do your quiz, and the practice quiz and homework before you take the test. You are pretty much basing it on data, but you still don't know for sure. So that is subjective. 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. So that's empirical. What happens is we talk to people, right? You get those awful phone calls in the middle of the night asking you from pollers. They're asking you all kinds of questions. And based on that, that's how they decide what's going to happen the next voter that they're talking to. So that's empirical. Then the probability of winning a 1,000-ticket raffle with one ticket is 1 over 1,000. So that's a classical probability. Okay, this one always gets me, so I wanted to show it to you. So this is a homework problem. It says classify the following statement as an example of classical probability, empirical probability, or subjective probability. Explain your reasoning. So it says, according to company records, that's what I don't always read. You have to read the whole problem. The probability that a washing machine will need repairs during an 8-year period is 0.25. Okay, so since it says according to company records, that means it's going to be empirical because that's based on what they've observed over time. And so the stated probability is calculated based on observations from the company records. I always want to make this subjective, but it's really not. They have data from all that time that they can make an estimate. All right, so this is very, very important. The probability of an event has to be between 0 and 1 inclusive. It can be 0, it can be 1, and it can be anything in between, any fraction, any decimal in between. However, it cannot be negative, can't be less than 0, and it cannot be greater than 1. Okay, so 0 would be impossible. That would be like when we tossed a 6-sided die and we were looking for a 7. Not going to happen. That's impossible. 0.25 here is unlikely. In the middle, you have an even chance. That's like tossing a fair coin. 0.75 is likely, and 1 is certain. Unusual means that it's going to be very close to 0, and we'll get to that in a little bit. All right, let's look at complement. So complement, if you have an event E And then you're looking at the complement. What we do is we put this little dash up there, right? It just means not E. So let's look at this sample space, excuse me. If E is heads, then the complement of E, or sometimes we call it E naught or E prime, is not heads. So of course, in this case, that would be tails. So what happens is over here, the probability of E plus the probability of not E has to equal 1 because there's nothing else left, right? So for heads and tails, the probability of getting a head, if we tossed a fair coin, would be 1/2. The probability of not getting a head, in other words, getting a tail, that would also be 1/2, and that has to sum to 1. And we're going to need this later on. So it's very important that you understand the relationship between E and the complement of E. Okay, so here's another example. So the event E is going to be rolling a 6. We roll a 6-sided die. Of course, there's 6 outcomes, right? With a 6-sided die, we have 1 through 6. E is only rolling a 6. Therefore, the complement of E is everything else. So that would be rolling 1, 2, 3, 4, 5, right? And so if we look at probabilities, the probability of E, or the probability of rolling a 6, is going to be 1/6 because there's only 1 6 on one side out of 6 chances. So the probability of rolling a 6 is 1/6. The probability of not rolling a 6 is everything else. And so there are 5 other sides. Therefore, the probability would be 5/6. And notice if I add those two together, I would get 6/6 or 1. Okay, that's very important that the event and its complement sum to 1. Well, the probability of the event plus the probability of the complement is equal to 1. Great. So this is an example of where knowing that relationship helps you get through the work a little quicker. This is that same frequency distribution where it has the ages in the first column and the frequency in the second column. And these are people who use social networking sites. And we want to know the probability of randomly selecting a social networking site user who is not 23 to 35. Okay, so you have 2 choices. You can come over here on the left-hand side, and you can just add up everybody who is not 23 to 35. So I took the 18 to 22, 36 to 49, 50 to 64, and 65 and over. I took all of those frequencies, added them up, put them over the total, and I got 0.68. That's fine for this one because there's only 4 numbers. But if I had 100 different rows in this frequency distribution, that would be a royal pain to add up 99 numbers. So what I can do instead, because I know the relationship between an event and its complement, so that would be not, I could have just taken 1 minus the probability of a 23 to 35-year-old. Okay, by doing that, the work's a lot easier. I take 1 minus 312 over 975, and notice I get the same answer. So this would be 1 minus the probability of not 23. Oh, I didn't do that right. I take that back. The probability of 23 to 35. So it would be 1 minus the probability of 23 to 35, and that would give me the probability of someone being not 23 to 35. All right, last problem. Just because this gets a lot of people in the homework, I wanted to remind you about a box and whisker plot. So in a box and whisker plot, we have a lot of things going on, right? But we have a minimum on the left-hand side. That's our minimum. We have a maximum all the way on the right-hand side. And then each of these lines of the box give us our quartiles, right? So Q1 is this first line, Q2 is the second line, Q3 is the next line. In other words, we have 0.25 in between each of these dots, right? Between the minimum and Q1, that is a quarter, so it's 0.25. From Q1 to Q2 is another quarter. From Q2 to Q3 is another quarter, and finally Q3 to the max is another quarter. Okay, so well, let's see what they're going to have us do here. So notice that with this one, they gave us the box and whisker plot. They also gave us the numbers associated on the number line with each of those, right? So 14 is the minimum, 22 is Q1, 35 is Q2, 54 is Q3, and 96 is the max. Okay, so now that we've done that, let's look. So the probability that a stock price is less than $22. Okay, so the probability that the price is less than $22. Well, 22 is sitting right here, right? So if it's less than, the probability that it's less than 22, I only have one quartile. So that would be, so I'm going to answer 0.25, right? So I'm looking at less than 22. I only have one quarter sitting there, and so that gives me the 0.25. All right, let's look at the probability that the price is between 22 and 54. Okay, well, 22 is right here. 54 is right here. And so the distance between these two, when I look at quartiles, I have two quartiles, right? I have 0.25 right here, 0.25 right here. So that's going to give me 0.50. All right, and then finally, the probability the stock price is 35 or greater. 35 is sitting right here. If I'm going to go greater, I actually hit two quartiles along the way. So again, it's 0.50.